Good evening. It is Wednesday, April 5th, 2023. So this is another aspect of our high school engineering design project. So this was ThermoElectric module. We're going to have a cold plate. I think the application was they wanted to make a seat cooler to put on a chair if you're a gamer to cool your seat. I think that's what it is. So we had come up with a method of mounting the thermoelectric cooler, and we went over that in a different video. So basically it was a metal cold plate on top, which let's see if we can get. Alright, so metal cold plate on top, air goes in this way, there's a heat sink and fan. The fan draws the air in, blows the hot air out this baffled side. Yeah. So this is the bottom view. I guess it's worthwhile to take this off just so you can see. Those are just baffles to isolate air chambers. So here's like the stack. There's a thermoelectric module, these wires. There's a heat sink on the hot side and a fan. Here's the data sheets for this thermoelectric cooler. And here's some graphs for heat load, voltage, current. We're not going to use these because it's 122 degrees F for the hot side. I think we're going to be closer to 80, 85, so we're going to use these two graphs. And it's a DC device, so polarity matters. Current going in, coming out will make one side cool, reversing it will cool the other side. And it's about 1.5 inches by 1.5 inches, 1/8 inch thick. So with this video, I would hope to show is the other video showed the mechanical, thermal and mechanical, how to mount it. This is more of the electrical circuit and the thermal circuit to understand that. So here's our thermoelectric module, our 1.5 by 1/8 inch thick. It has two wires coming out, a red and a black, and it gets connected to a DC source, a battery, which has a current in amps that goes through an effective resistance of about 2.5 ohms. So the more current that goes in, the more that you increase the voltage across this resistor, you get more current through that effective resistor. It gives you more heat load that you can draw out. More current correlates to more heat load out. And there's also this part here where you're putting in electrical power, so there's a heat that has to get dissipated just from this load here, not whatever load you're bringing off the cold plate. This is in addition to, so there's two parts of the heat. You have the heat that you're trying to dissipate from your cold plate, and you have the heat you need to dissipate from the amount of current that you're putting into this unit. Maximum voltage, they said, was 14 volts, and the maximum current is 6 amps. Ohm's law, I equals V over R, so the resistance is effectively fixed at 2.5. You put more voltage in, you're going to get more current. And you know, I'm not the thermal person, so I watched some videos and read some stuff, so this is what it looks like to me. Is that the Q dot load, Q dot is the rate of heat flow from the top from the cold surface to the ambient air here. And then this Q dot, heat flow, comes this way. In addition to the heat flow, like voltage and current, we have temperatures comparable to the voltage, and current is comparable to how much heat flow you have going that you can do. So in this diagram, this is a thermoelectric module. Up here is the cold plate. This is where we want this to be cold up on top where we sit. Below we have a heat sink and a fan, because this is our hot surface. This is going to be cold. This will get hot as the heat comes through, and we're dissipating the heat we put in. So the heat has to come out the bottom through the heat exchanger, heat sink, and the fan. So these are temperatures now. So ambient air, we're saying, is probably going to be like about 75 degrees, which like what the room is, and that's 24 degrees C. Where the heat sink meets up with the thermoelectric cooler, that's called T hot, and I'm saying there's probably going to be at least 10-degree difference between those two. It's probably a lot more. I don't really know until we measure it. So 85 degrees Fahrenheit is 30 degrees C, and you can see here it has a 138 degrees F, which is 138 degrees C max, which is 280 Fahrenheit max. Like, this surface can't get hotter than that or you destroy the device. That's why you need to put a heat sink on it. You just can't run these things without a heat sink on the hot side. Up here we said the top of the cold plate where you're going to sit, maybe let's call it 65 degrees Fahrenheit, which is 18 degrees. You can see that in there. 18 degrees Celsius. And there's probably going to be like a 10 degrees Fahrenheit difference from what the cold plate will have to be in order to get this to 65. This is probably going to have to be 55 because there's going to be some thermal resistance through here. So we're going to say that the cold side of the thermoelectric module, thermoelectric cooler, is going to have to be 55, which is 13 degrees C. So we're saying that the delta T, the temperature difference from the hot to the cold side of the thermoelectric module, is going to be T hot minus T cold. We thought it's 30 degrees C minus 13 degrees C is 17, rounding up to 20 degrees C. So that's our temperature difference, delta temperature, that we need. So we come over to our charts. So here we have 20 degrees Celsius, and then we go up to find the current that we can use and what's the max. So I guess we have to come up here at 20 degrees C, 12 volts, 14 volts max, but we're going to say a 12 volt battery we're going to use. So at 12 volts and 20 degrees C, we're at the 4.5 amp curve. So we can, in theory, 12 volts, 4.5 amps will give us 20 degrees delta. So down here it's 20 degrees delta, and we said we're going to use 4.5 amps, and we come across and we're saying it's about 35 watts of Q dot. So heat flow in watts is about 35 watts, which says, we put it down here, so let's just do this. So we can get 35 watts of cooling power, a delta T of 20 degrees C. We're going to have 4.5 amps at 12 volts. So we'll put 12 volts in. It'll cause 4.5 amps to flow through there. We're going to be able to pull 35 watts off of that cold plate, keeping this at 65 degrees, and the bottom will be at ambient temperature. We also have 4.5 amps times 12 volts power dissipated, so we have to dissipate both of these heat power. We will have to dissipate both of these heat loads through the heat sink and fan. Alright, I kind of chose 12 volts because I'm thinking I don't have a big enough lab bench power supply, enough current at 14 volts, so we're going to use a car battery. So we're going to do 12 volts, and we're going to use 6 modules, 1, 2, 3, 4, 5, 6. So electrically we're going to put them in parallel. Thermally they're going to be in parallel also. So we have one here, we're going to put one there, one there, one there. So thermally we're going to be pulling, we're not stacking them on top of each other, so they're not in series, they're going to be in parallel with the cold plate. So thermally in parallel, electrically in parallel initially. So this is one module, a resistance of 2.5 ohms. We want I thought I said 4.5. I guess it's 4.8 amps through it. All right, from 12 volts. I probably should go back and check my math. Anyways, so I have 4.8 plus 4.8 plus 4.8 plus 4.8 plus 4.8 plus 4.8 amps. I need approximately 30 amps at 12 volts. So a car battery would be able to give us 30 amps. Electrically, put all these in parallel. We'll get a delta temperature of 20 degrees C, 4.8 amps per module, 12 volts per module. The Q load should be 6 times 35 because we have 6 of those, and each of them can pull 35 watts. Should give us 210 watts. Right, that's what we got from the graph. In addition, we have our electrical load because we're putting power into it. So 6 times 58 is 345 watts. So this says 12 volts, 30 amps. We have to get rid of 345 watts of power, and we can pull 210 watts off of that cold plate. So you could put a 210 watt light bulb on that cold plate. Should be able to pull all 210 watts and keep that at 65 degrees. And we also have to get rid of this extra 345 watts of heat power. So that would be like the first test. Hook it up in parallel. You have some massive cooling you can get. And see what temperatures we can what we get, and then we can take some units out. If we need less of a heat load, or we have less of a heat load than we thought, or the temperatures aren't right,